your story for concurrency. Sorry? Can't hear me very well. Better? So, who am I? I write a bunch of gems. Dolly and Memcache clients, Rackfire pool, connection pool. I think of myself as a hobbyist researcher, and I tend to focus on scalability and performance. Now it's too loud, isn't it? In the past, not that better. I did a lot of work with fibers and EventMachine a year or two ago, so you might have heard my name there. Day-to-day, I pay the bills as a technical lead at Perham, which is a web development shop in San Francisco and LA. So, a quick Ruby history. I got into Ruby through Rails, and I love Ruby because it is a fun language to program in. And I think most of you probably would agree with that statement. I did not get into Ruby because its implementation is awesome. Ruby has some serious performance and scalability issues behind it. What this talk is not, it's not a shootout deathmatch between various concurrency options. These are all tools in your toolkit, and knowing them helps you understand when to use what. Threads also have this stigma because they're sort of associated with Java, but using threads doesn't mean that you're going to be a Java programmer. A thread is just a tool to solve a problem. Two definitions I want to make sure everyone understands is the difference between concurrency and parallelism. Concurrency is just being able to do two operations at the same time, or in tandem, I should say. Parallelism actually requires two CPU cores because you're doing two things exactly at the same time. So as you can see there, that I've got the blue and the red are two different operations. In both cases, they're happening concurrently, but only in the bottom case are they actually truly being done in parallel. Your operating system gives you only two primitives for concurrency: processes and threads, and that's it. Everything else that you may have used is just layered on top of those two. By themselves, they're very easy to use. It's very easy to spin up in processes to perform in different jobs. It's very easy to spin up 10 threads to do 10 different things at the same time. The problem is when you want to communicate between them. When you want to coordinate between those independent units of execution, you run into problems very, very quickly. There are two ways to communicate between threads and processes. Two fundamental mechanisms, and that's sharing data and copying data. And when you break it down, it kind of looks like this. This is a very general rule of thumb, but if you share data between threads, it's going to be more efficient than copying data between processes. So, since our scalability and performance, since that's all about efficiency, in general, we're shooting for the most efficient quadrant. Your operating system probably follows POSIX standard. In 1998, defined various mechanisms for doing IPC, which is inter-process communication. Four pretty well-known mechanisms are pipes and sockets, shared memory and files. In general, that breaks down into the graph like this. Pipes and sockets copy data between processes. Shared memory and files share that data between processes. So threads, I contend, are much more efficient than processes, especially in the Ruby world. But POSIX never defined any mechanism for communicating between threads aside from just variables. Unfortunately, and this is how it breaks down, obviously, it breaks down into that fourth quadrant. But unfortunately, that means we have to use locks. And nobody likes locks. At least I hope nobody likes locks. If you like locks, let me know. I'd like to talk to you more. And so let's go back to remember what I said about Ruby. Runtime efficiency isn't the only goal in the Ruby community. I think if you wanted runtime efficiency, you would have done the Twitter thing and gone to JVM or C or something like that a long time ago. We're in Ruby because it's a fun language, and we don't want to lose that fun. We don't want to lose that ease of development. And locks make development horribly, horribly unfun. I assume most people here have used locks before, but they're very hard to get right. They're non-deterministic because you simply don't know when you're going to context switch between processes and threads. They don't scale. They become bottlenecks at points of contention. They become bottlenecks in your process. This is a benchmark that I wrote just to show that contention in locks. In the first block of code, we have a single thread which is just incrementing a counter 10 million times, grabbing the lock each time. In the second block of code, I'm using 5 threads and doing the same thing. Basically, each thread incrementing that counter 2 million times. The results are kind of interesting. In Ruby 1.9, there's absolutely no difference in runtime. It takes 4 seconds in both cases. And that's because Ruby 1.9 has this guilt. Only one thread can run at a time. And so there's no thread contention. Now, in JRuby 1.6, because it has truly parallel threads, you get massive lock contention. So using 5 threads to increment that counter causes a massive slowdown as the threads contend for that mutex. So, this is the most important slide in my talk. I was talking to Adam Keyes yesterday, and he said, if that fourth quadrant was a movie, it would star Nicolas Cage, and it would involve a conspiracy at the highest levels of our government. Thanks for letting me know. That's the quadrant that the POSIX standard doesn't want you to know about. And yet no mainstream operating system or a mainstream language really does anything with that quadrant. And I think that's a shame, because threads are much more efficient than processes. Copying data isn't bad, and copying data means that you don't have to use locks. And so by focusing on that quadrant, I think we can uncover a lot of tools that really make development a lot easier and a lot more scalable. But
actually, I'm not sure right in your statement. Windows has thread local storage. And I'd have to go back and check the API because it's been a few years, but I'm pretty sure that you can use that API to copy between threads.
Thread local storage means that you can access that storage from that thread only. You can't, I don't know that you can use it as a communication mechanism.
What I was saying is I think there's kernel call to apply to copy between one thread to the other.
I'm not familiar with that. Windows APIs and like that. So it's a general statement. Let's just leave it at that. So what can we do to learn about that quadrant? Go outside the mainstream. There are several languages that have offerings in that area that are very interesting and which can help us decide maybe a better course for Ruby. So Go is a great little language from Google, and it's got this thing called Goroutines in it. Goroutines are really cool. I really like them. They're just anonymous functions. You spin them up, and you can't get a handle to it. It's not like a thread where you knew it and you've got a handle to it in a local variable. Once you spin it off, it's gone. The only way you can communicate with it is through a channel. And so I've got a function here that shows a very, very simple example of using a Goroutine to perform a calculation and to pipe the result back to the channel. So you can see on line 2, we're creating the channel. On line 3, we use the go keyword to spin off that function. And that runs in a separate thread now. Meanwhile, the main thread on line 9 blocks on that channel waiting for a message to come back. And that message is just going to be that calculation that's performed on line 5, the value X. And then once that value is calculated and put on the channel, the main thread wakes back up and prints it out. It's a very simple model. I really like it. I think it maps really well onto a network model where I can't get a handle to a database, but I can open a socket to that database. So to me, this kind of feels like a socket where you're pushing messages onto a channel, or you're pushing messages onto a socket. And in Go, the runtime actually uses a pool of threads. So Goroutines actually can migrate between the threads in that pool, so that your Goroutine can be executed by any thread at a given moment in that pool. Actors is in the title of the talk, so no surprise that I was going to talk about them. But Erlang and Scala use actors as their main concurrency primitive. The idea behind an actor is that this is something that just executes asynchronously. It has a mailbox, and you send it messages to be processed. So in this case, I've got a very simple example where I've got a handle to an actor that I created, and I'm just pushing a hash onto it as a message, and it will do something with that message. Actors can be thread or fiber backed. You don't really know. You don't really care. You shouldn't care. Because again, those are low-level primitives that an actor is a higher level construct. And because you're copying data to that actor, there's no locking going on here. That's his copy. He gets a copy of the message. And if you take that message after you send it to him, he doesn't know that because he has his own copy of that message. So I want to take a look at some actor projects in Ruby just to quickly sort of cover the scene and maybe give you a couple ideas of what's out there already. Probably the most mainstream actor API out there is Actor.rb. It ships with Rubinius, and it does work on JRuby and MRI. So you just have to get the gem. There's another. They actually, Rubinius publishes a gem, just this code in it, that you can use on MRI and JRuby. This is an example of using the API. This is a very trivial example, so I apologize, but it's your typical ping pong incrementing a counter. On line 11 and 18, we're creating the two actors, we're spawning the two actors, and they're just going to loop receiving a message, and then they're treating that message as an integer, and they're just incrementing that message back and forth between them. So on line 25, the main thread kicks off the ping pong process with 0, and that just then ping pongs back and forth between the two actors until it reaches 100,000, at which time it just prints out the console and exits. A very simple API in principle. I found it very hard to use, though. It's not idiomatic Ruby at all. It's very procedural, and I think it's heavily based on the Erlang and Scala APIs. So it just doesn't feel like Ruby, and it was hard for me as a Rubyist to understand and to use. I actually had to have the author explain to me how to use it. But there's a lot better project. There's a much better project, Celluloid. Tony Arcieri is the author of Celluloid. He's, I think, well known in the Ruby community for his RevActor and Rhea projects. RevActor was his first take, his V1 of an actor API for Ruby. And Celluloid is V2. And it's a really nice API. It's object-oriented actor, so it's very idiomatic Ruby. And it provides basically asynchronous method invocation on objects. His implementation uses a mixture of threads and fibers under the covers. This is that ping and pong example, but done in Celluloid. You can see here we're actually defining two different classes, and we're including the Celluloid module. By including the Celluloid module, that turns this class, this object, into an actor instance. So down in 24 and 25, our main thread is actually creating those two actors and then kicking off the process on line 27. Note on line 28, it then blocks, the main thread blocks, waiting for the actors to finish. That's a nice feature of Celluloid where you can actually get some synchronization between the actors. But basically, they're just passing the message back and forth until they reach 100,000. At which point, the done symbol is signaled on line 15. So I really like Celluloid, if it wasn't obvious already. It's a very idiomatic Ruby. One limitation of it, that I think needs to be rectified probably, is the fact that every instance that you create is backed by a real thread, which means in Ruby, threads are a minimum of half a megabyte of memory. So every object you create basically takes half a megabyte of memory, which is very heavyweight, needless to say. So the Celluloid could use actor cooling. It'd be nice to have cooling so you could reuse actor instances. Girl Fridays, the third project I want to talk about. This is my project. It is based on Actor.rb, so it's layered on top of Actor.rb. But it provides background processing tools where you have a supervisor and then a pool of workers behind that supervisor. It also provides parallel batch operations, so you can give it a large amount of work, and it'll give that work to the workers, and then you can block waiting for the entire batch to be completed. It's designed as more functional than object-oriented. I'll show you what that means here in a second. And it's solely thread-based. So this is a simple example of using Girl Friday. I designed Girl Friday to be just very simple background processing for Rails applications. The idea being that in this example, in a Rails application, quite frequently you want to send an email when the user registers or signs up for your website. But you don't want to do that on the main thread that's processing for the request from that user, right? You don't want the block on that network. So you want to do the email delivery asynchronously. That's exactly what this is designed to do. So in this case, we're creating a work queue with 3 workers behind the scenes. And all those workers do is process that block that's effectively line 6. That's what I say when it's more functional than object-oriented. We're not creating any classes here. We're just passing blocks of work around. And on line 10, you would have something like you have in an active record model, where after we save this object to the database, we want to send an email. But instead of actually doing the delivery on that thread, we create the email and push it onto the queue. And then once that message goes to a worker actor, the worker actor actually calls deliver on it. So this is an example of the batch processing that Girl Friday provides. In our case, we've got a couple of URLs that we want to scrape, but we don't want to do that in serial. We want to do that in parallel because that's network I/O. So we create a batch with 3 workers and pass it the URLs to process. Each of those workers will execute that block for each of those URLs. And then what it returns, in this case, the count of the spans in the document, that will be the result for that entry. And so when we call batch.results, that actually blocks waiting for the workers to complete, waiting for the queue to be emptied. So that's a brief overview of actors in Ruby. There are some times where we do need to share data. And there are some solutions there that are a little off the beaten track and aren't really mainstream yet that would be nice to talk about. As I said earlier, this is what the POSIX standard sort of defines in the 80s. Life has moved on. In fact, we have 2 other possibilities that I'm aware of. Maybe you guys know more. We covered actors in that lower quadrant, but if we want to share data between threads, we have software transactional memory. Software transactional memory basically allows you to do what databases do on disk in memory. Allows you to mutate your data, but within the realm of the transaction, so that you can provide the ACI guarantees of atomicity, consistency, and isolation. Closure is gaining a lot of traction, I think, because it uses software transactional memory for all of its mutations. And so any programs you write in Closure essentially are guaranteed to be concurrent, highly concurrent, scalable. Note it doesn't provide durability like databases because we're not persisting to disk. And I heard yesterday that Charlie Nutter announced Clovey, which is he brought the Closure STM library to JRuby through his new Clovey gem. That sounds pretty awesome. I haven't really looked at it in depth, but that's definitely one thing I would recommend checking out. Atomic instructions are the other thing that I wanted to mention. They've been around for almost 20 years now. There's two atomic instructions that I'm aware of that are important. There's exchange, which allows you to swap registers atomically, and then there's swapping a register value with a memory location atomically. But more important, I think, is a compare and exchange, compare and set operation. Compare and set is the fundamental operation necessary to do optimistic locking. So once we have this compare and set operation, we can write higher level data structures that use compare and set to provide essentially software transactional memory. Unfortunately, I'm not aware of any code that provides atomics on MRI, but JRuby has access to atomics because the Java util concurrent package has atomics in it. So I wrote my 10 million counter benchmark with atomics. The first block, of course, doing it with a single thread, and the bottom block doing it with 5 threads. And the results are interesting. With 1 thread, I got 2 seconds. With 5 threads, I got 1 second. So why didn't it speed up 5 times? Well, it only sped up twice because I've only got 2 cores. So I can only do 2 things at once. But that's awesome. Getting a 2x speed up with 2 cores, that's linear speed up, and that's awesome scalability. What's up, Nick?
Can you please buy bigger machines for your demos in the future?
If Engine Yard wants to I'm happy to take any sort of 8-core Mac Pro that Engine Yard wants to provide. But that's awesome, and that shows the power of atomics right there. There's no contention at all. It's an extremely low level built into the Intel chipset, and it scales really well, at least for 2 cores. Now, to Dr. Nick's point, if I had 32 cores, I don't know that I'd get a 32 times speed up. That's usually it tails off, but for 2 cores, that's awesome. Java has, like I said, based on that compare and set operation, has 2 data structures that are lockless, a hash map and a queue. And these are great data structures to check out if you want to see how this stuff is done under the covers, how to provide sort of a higher level data structure built on these very low level primitives. So, in conclusion, concurrency. It's always hard. It doesn't matter what you're using. I don't care if you're using processes, events, threads, fibers. It's always going to be hard. You're always going to have race conditions. You're, communicating and coordinating is always going to be difficult. But the modern mainstream languages should provide tools and APIs that allow us to scale well and allow us to have fun when we're writing these systems. We don't want to lose that sense of fun in Ruby. So, to that end, what do we need to do? I wish Ruby had a standard Actor API. Actor.rb is not a good API. We need something different. Celluloid is an awesome API. But I'd love to see all the implementations come up with sort of a standard API that they all agree on. I'd love to see concurrent data structures. I'd love to see someone port those Java structures to Ruby. I'd love to see a software transactional memory implementation for Ruby. Java, again, has several STM implementations. Like I said, Clody yesterday, I just heard about yesterday. There's another one called Multiverse. These are Java APIs that someone it's just waiting for somebody who wants to build a new cool gem to wrap the Java API with a Ruby API. If you want to do more research in here, there's a couple really interesting projects. Perham is a Persian word for tapestry, I think. Basically being a play on fiber. It is high performance, lightweight actors for Java. And they can spin up hundreds of thousands of actors in a process. I'm not sure why you would do that, but they do it. Disruptor is a really interesting project where this team that was building a trading exchange program, they were getting about 50,000 operations per second, and they decided that that wasn't nearly good enough, and so they dropped their main design, which used queues and locks, for another data structure that was lockless, and they got a 100x improvement in speed. They can do 6 million operations per second now on the JVM. It's just an incredible story. And then, of course, actors in Scala and Erlang are the old standbys if you want to learn more about actors in general. That's all I have for you. Thank you for listening. I'm happy to take questions.
So your Girl Friday library actually looks relatively reminiscent of the dispatch library available in Actor.rb. I wonder, have you looked at that or GCD in general and thoughts on going in that direction?
So the question was, the Girl Friday library looks very similar to the dispatch library in Actor.rb?
Yeah.
No, I've never heard of it actually. I'll take a look at it. You mean the Grand Central project?
Yeah, it's based on the dispatch, Grand Central dispatch.
Yeah, I mean, I've heard of Grand Dispatch only because it kind of made waves back, I think, when Snow Leopard was introduced. But I've never looked at it in any depth. But I'll take a look at it. Yeah.
So do you have any books that you could recommend as sort of a practical guide on doing concurrent processing? You know, I did some back when I was doing my CS degree, but that was all POSIX 3 and that looked. And most of the books I found are very academic, very high-level overviews of the theory, and I was kind of looking for some sort of overview of libraries that might actually do this.
Nothing springs to mind. Does anybody have any books they recommend for pragmatic concurrency?
There's the Java Concurrency in Practice book is excellent. And it covers all of the, you know, it's a practical, it has some theory, but it's also a practical look at what Java can provide for. It's as listed, I think.
Yeah.
No question, actually. So you covered the technologies that are available to us as Rubyists for concurrency. Can you speak a little bit about how once as Rubyists we have access to either STM or concurrent data structures, how should having access to those things inform the way that we design our programs? Should we just use those data structures in the same way that we would use data structures now, or do we need to reformulate the way that we write programs to be more cognizant of how what we do affects the ability of our programs to be concurrent?
I think it's the latter. So what's really interesting about, especially to take a language like Clojure, the way that Clojure is designed, because it's immutable, you have to plan for every mutation that you want to do. And when you mutate data in Clojure, you don't just mutate it. You have to provide Clojure a prop, essentially, which knows how to do the mutation that you want to do, and then Clojure will do it for you. Because it's doing it within a transaction, if that transaction rolls back, it has to run it again. And it'll keep trying to mutate that until that transaction succeeds. So effectively, when you have something like STM, your code has to plan to mutate. It's not just a variable that you can willy-nilly increment and have it work most of the time, but that 1% of the time, when you get a race condition, then all of a sudden things blow up. So STM forces better practices around mutation of data.
You mentioned in the process category things like named pipes and just the pipe system call.
Yeah.
What experience or comments would you have about using those to communicate amongst threads?
Pipes and threads. To be honest, I've never done any pipes work at all. So I have no experience. Does anybody have any comments about using pipes with threads? Has anybody done it?
It works. Just you can do it.
Yeah.
Just use a queue though.
Yeah, you could just use a queue.
So yesterday at the Ruby 193 talk, we were talking about how a lot of the current experimentation is going on to see how they can improve multi-process performance in Ruby. It's looking for more efficient ways to communicate between processes rather than looking for more ways to do communication between threads. Just curious what your opinions on that are.
I think it's exactly the wrong direction. I think having an MVM where you have a different heap for each Ruby VM is exactly the wrong direction. It's all about memory efficiency. I put up a blog post on the Carbon 5 blog a week or two ago, basically where I improved Rescue's memory efficiency by 68 times. I had a client that had a large farm of Rescue workers, and it was using in total 68 gigabytes of memory. And I rewrote Rescue to use threads in JRuby instead of forking child processes. And we can now do that same amount of work with one JVM process using 1 gigabyte of memory.
That's very specific to JRuby. In MRI, you don't have this problem.
You can use threads in MRI.
Well, but you don't have to, and forking is actually efficient in that case.
No, it's
You
not.
fix the problem for JRuby.
It's not. It's not copy on write friendly.
Or you can disable the GC when you fork the process.
If you're disabling the GC, my friend, you're asking for trouble. Yeah, Ruby just does not have a good concurrency story. Forking processes does not work unless your garbage collector is copy and write friendly.
How does NVM differ from like Erlang's processes, multiple processes in one process?
So the NVM process is much heavier weight. It's an entire Ruby system, effectively. Erlang's processes are very, very lightweight structures. They're essentially, I believe they're essentially fibers, very lightweight fibers. So yeah, they don't really compare. Jeff?
I've always felt the problem with threads was the problem of accidental shared mutable memory.
Mm-hmm.
So do you have any advice on how to avoid the accidental issues?
There's not much you can do given that Ruby is a mutable data system. Best practices, trying to use STM or other type of systems for all the stuff that you do, or trying to use actor libraries and that sort of thing, so that you yourself are not writing code that mutates data. You are instead writing actors that use their own copies of that data.
How do you deal with the fact that the shared mutable memory can happen in a library that you're using?
Yeah. There's not, it's the same thing with monkey patching, right? How do you know a library is not monkey patching object to raise every time a method missing is called? Who knows?
Well, monkey patching is a little more deterministic.
Yeah.
The shared mutable memory problem is that it might happen. It might be happening and you don't know until you get 100 processes at the same time.
That's true. That's true. I don't think there's a good answer for your question.
I think that's part of the reason the MVM thing looks attractive, is that you avoid the shared problem.
But you're
it's a tough thing to do in Ruby.
Obviously, you're paying the price for that, though,
Yeah.
with non-shared heaps. And that's really what it comes down to, is making trade-offs. if you can afford the memory, by all means, use rescue and forking mode. But if you're paying for hundreds of machines on EC2, and you want to go down to 10 machines or one machine, sometimes you've got to do optimizations that cut corners. And you just hope that your testing uncovers any issues beforehand. Oh, way in the back.
Hi. So you mentioned that forking is not a good strategy unless you have a garbage collector that is copyright friendly.
Right.
I wonder if in your past project, if you were using RE and if it's not garbage collector friendly for some reason. Because I remember on the rescue presentation, like the blog post, they mentioned that they need to use RE specifically just because of the garbage collection.
Yeah, well, RE those guys have done a lot of work to make their garbage collector copy and write friendly. And you do definitely see some savings there. Obviously, RE's problem is they're still stuck on Ruby 1.8, and the Ruby world has kind of moved on from there. I'm using Ruby 1.9 everywhere. I haven't used Ruby 1.8 in over a year. So yeah, when I tend to have problems, I tend to move to JRuby. It's almost better in every way. Overheard. JRuby better in every way. Any others?